be mv squared over L cosine theta.
So, never mind, I see it. So you're saying those two problems are acceptable, like those equations?
Yeah, this one's okay, and then this one ignoring that, so. Those are the correct answers.
Why does it say and or any number?
Because if a 1/2 shows up, I mean, you're allowed to use pi or 1/2 or whatever you happen to use there.
So you put L cosine theta because that was what equaled the R over there, correct?
Yes, yes. Now, part D, other questions before we get to part D?
Where did that top equation come from?
This?
Yes.
We derived it in class, plus there's a couple videos, but this is centripetal acceleration. The magnitude of centripetal acceleration is, there's two different formulas that we could use.
And was that for part A?
Part A was the force diagram.
So that's another.
That shows
equation.
up right here when we put it v squared over r. Because we had tension times cosine of theta is mass times acceleration, and then we use v squared over r for A. Other questions? All right, so part D is, the way I originally had done it was far more complicated. That's why I think put down that it's the hardest problem on the test. It's not as complicated if you happen to see the trick. Yeah, originally, multiply both sides by cosine theta, so I got tension times cosine squared theta equals mv squared over L. And then I can solve for tension with that, so then we get mg over sine theta cosine squared theta is equal to mv squared over L. I got a sine theta and a cosine theta. It just gets way complicated.
So why are you squaring the cosine?
If I multiply both sides by cosine of theta.
Oh,
However, I know M, so I know V. Let's see, I give you mass, I give you L. It's 4. V. All right, so I have V, so what do I know? So I know M, L, V. So theta and tension are my unknowns.
So how did you get, G?
It's the acceleration due to gravity.
Oh, the 9.8.
This one happens to take place on Mars, so 3.8 meters per second squared.
Oh, I see. Thank you.
So, I have tension cosine of theta is equal to mass times the centripetal acceleration. Well, the centripetal acceleration is also omega squared r, which is m omega squared L cosine theta. This might be more, this might not be as short as I was thinking.
Where did you get that equation from?
This?
Yes. Yes.
That's from right here. If I use the other formula for centripetal acceleration, use omega squared r.
Oh, okay.
Why is it times L instead of divided by L?
Sorry, why is it times L cosine theta?
Yeah, instead of divided by L cosine theta.
Oh.
Yeah, that's what, that, never mind.
Okay. Might have to. And I know that tension from that first equation is equal to mg over sine theta. So therefore, we have mg over sine theta is equal to m omega squared L. Mass cancels out. Yeah, this is not gonna be as nice as I was thinking. Okay. All right. So solving it the way that originally intended, so I guess I had thought through this one a little bit more than I remembered. From the equation over there, we have tension times cosine of theta is equal to mv squared over r. Oh, over L cosine theta. And we have tension times the sine of theta is equal to mg.
So those questions on that side doesn't apply now?
I mean, this is all valid, but it's just not gonna get us where I wanted it to do. I need to somehow get my variables together, so I'm gonna solve for tension in the second equation, which is basically right there. Plug into the first one, so I got mg cosine theta over sine theta, that's my tension, is equal to mv squared over L cosine theta. Mass cancels out, just like we had over there. So G over sine theta. So G cosine theta over sine theta is equal to V squared over L cosine theta. I need to get in essence, I'm solving for theta. I've got one unknown here, but because they're sort of captured in the trig function, it's a lot more difficult. So I'm going to basically cross multiply. So I have GL cosine squared theta is equal to V squared sine theta. And it's still not particularly obvious. I guess with calculators, there are other methods of doing this, but employing the identity that I mentioned in here, the fact that sine squared plus cosine squared equals 1, this tells us that GL 1 minus sine squared theta is equal to V squared sine theta.
Is that a V squared?
That's a V squared. Distributing, I get GL minus GL sine squared theta is equal to V squared sine theta. In essence, I've got a quadratic here. Taking everything over to the right side, I have 0 is equal to GL sine squared theta plus V squared sine theta minus GL. If this does not look like familiar to you, then why don't we just let x equal x equals sine theta, and it becomes x0 equals GL x squared plus v squared x minus GL. It is just a quadratic. We know the value of v, we know g, we know L. You can plug in and get numbers if you wanted to go that route at this point. And x would be negative v squared plus or minus the square root of v to the fourth minus 4 times GL times negative GL over 2GL. Plug and chug. You're going to end up with two answers here. So sine theta, which is x, is going to be one of two answers. Now, hopefully, one of those answers clearly is not going to be right. If we end up with something bigger than 1 or less than negative 1, that can't be a correct solution. Because sine theta goes from negative 1 to 1. And the other one presumably is the correct answer. So theta would be equal to the arc sine of whatever that is. But that's why that's the toughest problem there. Questions?
Does that say theta equals a sine?
Yes, arc sine. Right off arc. On your calculator, for most of you, it'll be sine raised to the negative 1.
Is that a squared in between the parentheses?
The squared in here?
No, in the a sign.
No, that's the head of the arrow.
Okay. And then what is the sine theta below it for?
All right, so let's actually do the numbers then.
It just wasn't, like in order somehow.
All right, so we have x is equal to this.
Mhm.
We need plugging numbers at this point. I know that v is 4 meters per second, given in the problem. So we have negative 16 plus or minus the square root of 256 minus 4 times GL. That was L. L was,
1.22 meters.
all right. And G is 3.8 meters per second squared.
And
So that times that squared times 4 is something.
you said 1.22 times 3.8.
Or around 20.
So you said 1.22 times 3.8 squared?
Yeah, but multiply first and then square it,
Yes,
and then times 4.
I got 85.96.
Okay. And so, and then 2 times GL, so that times 2.
You said that times what?
1.22 times 3.8 times 2.
9.27.
So our two solutions. Negative 16 plus or minus that. Doing the fancy cipher here. So square root of 0.96. Carry the 1. 341.96.
The positive one is 0.2688. And the negative one is negative 3.721.
2.721.
3.721.
3.721. All right, so we have two solutions here for, remember this is solving for x, which is just sine of theta. So I'm making the claim here that the sine of my angle equals 0.2688, or the sine of theta is equal to negative 3.721. I know this cannot be the solution. You try it on your calculator to solve for theta there, you should get an error. Eliminating that one, we're left with the sine of theta is equal to that. In other words, theta is equal to the arc sine of 0.2688, or as I on my calculator, a sine of 0.2688. Actually, on my calculator, 0.2688, and then hit the arc sine button. Or on your TI-8 or whatever, you get inverse sine 0.2688. Say it again.
15.6. $15.5953.
Units,
You misinterpreted this, the look.
degrees.
Degrees. Yeah. If you don't put units down for the angle, it's assumed to be radians. Now, it's possible 15.6 radians is the same as 15.6 degrees, but that would just be a coincidence. All right, questions? All right, let's just take a small little break here, stretch legs, come back. Let me make sure I get to the most complicated problem before we do the other stuff. That's 5. Yeah, there's 3 problems left, but take a break, stretch legs. Preferably don't smoke them if you got them. On the master set, the problem that was similar to this, I asked for the equations of motion for 2 of the masses. And this one, I only asked for the equations of motion for m sub r, which is the ramp there. Acceleration is to the right, so what coordinate system would make the most sense?
The normal one, standard, IIJF.
Yep. Look at my pocket. Nope. Somewhere there's a pin around here. So if that's set up as our coordinate system, do we need to decompose anything?
Yes.
Which ones do we have to break up?
Y sub 2 and F sub 2.
Yep. Everything else is perpendicular and horizontal. F2 is probably going to be the simpler one to do, because I know F2 is going down at some angle alpha. So I just need to break that up into its components here. Whatever I'm breaking up is the hypotenuse, so this becomes F2 sine of alpha and F2 cosine of alpha. Normal force associated with that friction is perpendicular to it, so when I break it up, well, flip the trig functions here. So if that's F2, if cosine theta was the horizontal, ooh, that's a, take off that, alpha. So this horizontal here would be the sine, so this is y2 sine of alpha and y2 cosine of alpha. So in essence, I got some object here, I got a big F going off to the right. I got FR going off to the left. I got WR going down. Got Y sub R going up. Friction, I've got F1 cosine alpha to the right and F1 sine alpha down. And then normal force is down and to the left. So then I have y to, or F1 there, it's F1 or F2, it's F2. Which would be F2 there. Cosine alpha down and y2 sine alpha to the left. Yes?
Can you explain how you related alpha to the normal force triangle?
To the normal force?
Yeah, the purple triangle,
Okay.
the one on the top. front.
Right. Well, but you're good with this?
Yeah, that makes sense.
All right, so the quick and dirty method is the fact that since these are perpendicular to each other, the trig functions would switch. So horizontal is cosine here, horizontal will be sine here. But let's say your brain's not working that way when you, on the day of a test.